Greetings, I'm Zach. I just found out yesterday I'm doing this, so sorry if the slides are a little rushed, hence the default font and background. But I don't know, it's not a difficult language to talk about. It's kind of I don't know, Clojure is a language where you can wing it pretty easily, very naturally. So I'm Zach Oakes. Been using Clojure for over 2 years. I've never been paid for it yet. These are my projects that I've worked on in that time. It's in my spare time. I'm not really a normal Clojure programmer, though. I mean, my understanding is Clojure is mostly used for like server-side and browser-side development. I basically never have done that. My first one was an Android app written in Clojure. Don't really work on that anymore, but Nightcode is another project I made. It's a Clojure IDE for beginners. It's written in Clojure. It's a client-side tool, user interface written in Swing, that kind of thing. And the last two are the work I've been doing with Clojure game development. So again, I mean, client-side GUI programs, games, not typical stuff to use Clojure for, but it's fun anyway. So Clojure, while standing on one foot, how do you define it? This is straight from their website, and I actually like the definition. It's 4 parts. It's a Lisp for functional programming, symbiotic with an established platform, and designed for concurrency. That's pretty much the highlights. So before I actually get into it, though, you read those 4 things. It's not that they're meaningless, but it doesn't really present much of a call to action, like why should I care? And I think people get a little bogged down in the details sometimes. So, the way I look at it, there are a lot of ways you can stratify languages. You can look at, interpreted versus compiled, static versus dynamic, functional versus imperative, that kind of thing. And, those are all useful things to look at, but the way that I separate languages in my head most often is this: practical versus academic. And neither of those are meant to be pejorative terms. Like, I like practical and I like academic. Practical languages I think of as languages that everyone uses but nobody likes. And academic is languages that are beautiful, they have incredibly powerful abstractions, but for one reason or another, people just aren't really using them, especially in industry, very much. And, there's a lot of lament about that. So one of the reasons I really like Clojure is that I can't figure out how to classify it. It seems to have both. If you look at those 4 things I just mentioned, the first 2 seem to be pretty academic. It's a Lisp and it's functional, but the last 2 seem to be more practical. So symbiotic and an established platform, that just means it runs on existing runtimes. It runs on the JVM, it runs on JavaScript. And designed for concurrency, again, I mean, simple constructs for concurrency, that's not a theoretical problem. People need that. So that's the main reason I like it. And since I like this breakdown, I thought I would just visit each of them individually and talk about them. So the first one is the fact that it's a Lisp. And, depending on your background, that's a good thing or a bad thing. So I'll start with what I call, nobody else calls it this, but I call it the Big 4. It's the fundamental data structures of Clojure. And the first one is, of course, the list. And the second one is a vector. The third one is a hash map. The fourth is a set. And you might call these the fundamental data structures of computer science in the sense that most problems can be solved pretty efficiently with just these 4. data structures. So the list is the linked list, each item pointing to the next item. There's no table or index of items that it keeps track of. The vector is similar to an array in other languages, so that's the data structure that stores things sequentially and keeps an index. And I should mention linked list is fastest at prepending items at the beginning and modifying things internally. The vector, because it has an index, is fastest at random access and adding things at the end. The hash map is a key value store, as you can see. So similar to a dictionary in Python, associative array in PHP, at least conceptually, I don't really know how they're implemented. So that's where you store pairs of values. And finally, the set, probably the least used of the four, but when you need it, it's useful to have. It's the data structure that only allows one of any given value, so it prevents duplicates. And it also does not keep track of order, so you have to keep that in mind too. Neither does the hash map. So fundamental data structures, and as with any Lisp dialect, code is represented by the first one. So code is just a series of lists. Doesn't matter if you're adding numbers, conditional statements, or defining a symbol. It's all, at least on paper or digital form, before it's read, just a series of lists. So first one, it's going to evaluate it at runtime. It's going to see that the first item is the plus function. It's going to run it, and the return value is what it is replaced with. And same thing for everything else here. Notice the if statement there is embedded inside the print statement. So, if you come from C-like languages, you may not be used to the idea of an if statement as an expression. I was not, because Clojure was, I came from that background of C, C++, Java. So it's one of those moments when you're like, wow, that makes a lot more sense. So, yeah, everything is a list. And, it's not always clear what the advantage is of that. Why represent code as lists? You don't have to, obviously, most languages don't. Are entirely too many words on this slide, but most languages have a distinct syntax for code, and there's nothing necessarily wrong with that, except that the compiler needs to have special tools to parse it. And those tools are typically not available to the language user. So that's the fundamental difference. When you're using a Lisp dialect, libraries have the same power that the language authors have. And these are some examples of Clojure libraries that implement things that most languages would not be able to implement as a library. So core async provides asynchronous channels similar to the built-in feature in Go. Core typed provides static type checking, which of course is built into a lot of languages. Core logic provides logic programming. Normally when you want that, you need to use a completely separate language like Prolog. So in all three cases, these are just libraries. And they, in fact, they're just dependencies. You just add it to your project and it works. So it ends up being a good example of the power that this kind of syntax provides. And homoiconic is the technical term for that. So the specific technique they use to do that is macros. So the first one is just a normal function. Defn square is the name of the function. And it takes a vector where you list the arguments. In this case, it just takes one argument, unhelpfully named n. And then the last part there is just the body of the function. So what do you want it to do? And this is just multiplying them together. So when you actually use it, of course, it's just square 2. And at runtime, it provides you with your answer. So if you were to take that defn statement and just replace defn with def macro and leave everything else the same, it would actually work the same, at least in this particular usage. The only difference is that it would run it at compile time. And the end result is that when the program ran, there is no concept of square. There's just a 4 that's sitting there as basically a literal. This is not normally what macros are used for, though. They're normally used to return a list. And the reason why is because, as we went over, the syntax is nothing but lists. So if a macro returns a list, then at runtime, it'll be evaluated and run as a function. And that's the facility used by those libraries that I just mentioned to morph the code in all sorts of different ways. So I think the specifics of macros are beyond the scope of this talk, but you can dive into that rabbit hole as much as you want. But that's the basics. So now this is something that was never explained to me since Lisp was my first. Clojure was my first Lisp. And so one question I had that nobody could seem to answer is why specifically is code represented as lists? I mean, why not print hello world? Why not represent it as a vector? Or even a hash map? Or a set? I mean, what is it specifically about a list that makes it so special out of these 4 fundamental data structures? Well, let's rule out sets first, because that doesn't really make sense. First of all, sets don't maintain order, so if you wrote a language that was represented as sets, it would work some of the time. Because, you don't know what the first item is going to be. It might be the function name, or it might be hello world. At runtime, you're not sure. There's another problem with this. Can anybody see the other problem with one of those examples, why it would not work? It has to do with the nature of sets. Yeah. Yeah, exactly. This language would not be able to add 1 plus 1 because this would actually be a reader error in Clojure. It wouldn't even compile. Remember, sets are not allowed to have distinct or values that are the same. So this would obviously not make sense. Now, what about hash maps? This kind of looks interesting. You could probably get away with that to a certain extent. Every argument would have to have a keyword as a name. I guess I didn't mention that. The blue things there are keywords. That's a data type in Clojure. You don't see it in all languages. It's very useful and very common in Clojure. It's not just using hash maps. It's basically kind of like an enum in some languages. It's a really lightweight label. It's used everywhere. So anyway, if we were to make a language based on this, it would kind of be like Objective-C, where you have to have named parameters for everything. And, the first problem is just it's really verbose. I mean, look at adding 1 plus 1. It doesn't look very fun. And the other thing is variadic functions wouldn't really be possible. So variadic functions are just functions that can have a limitless number of arguments, like a plus function, for example. It'll just take however many numbers you want. So you can't really do that if you represent code as maps, because you would have to come up with a unique key for each of the arguments. I think Objective-C gets away with that by actually departing from its normal syntax. So it has variadic functions, but it's just like a comma delimited list, so it's kind of cheating. So what about vectors? That one is the only alternative that kind of makes sense. You could probably do that. In fact, there was an April Fool's joke along those lines. Some of you might have seen. Someone pretended to invent a Clojure dialect that used square brackets for some reason. I think it was just for aesthetic reasons, but you could technically make a language where the syntax consisted of vectors. It has all the qualities you need. It maintains order. It's sequential, and so on. So traditionally, when I ask why don't we use vectors, people would just tell me, well, it's just tradition. We've always used lists. But I actually think that it makes sense if you look at the data structures. You don't really need random access when you're parsing code. You can parse code sequentially. And random access is one of the reasons you use vectors. Also, vectors are pretty slow at modifying internally, and in Lisp you do that all the time, of course, with macros. So in a way, I think linked lists are the perfect data structures for representing code. All of this is just me BSing. I'm not entirely sure if this is the reason that Lisps use linked lists instead of the other data structures, but it makes sense to me. So now, all that being said, lists are actually not that special in Clojure. This is something that makes it pretty different from other Lisp dialects. Is Clojure, it kind of demotes lists. So in most Lisp dialects, lists are the be-all, end-all, so to speak. Other data structures are, in a way, treated as derivative. But in two important ways, Clojure departs from this. So the big four data structures, as you've already seen, have their own notation. They have their own literal syntax. And this is already something that you don't see in other Lisp dialects. Something that rustles the jimmies of a lot of traditional Lisp aficionados. They don't like the notation sometimes, because it is a big departure from normal Lisp languages. But not only does it make sense from the standpoint that linked lists are really not that special, but also from an aesthetic standpoint, it does kind of dampen the paren overload. So this is a complaint that people often have with Lisp, is too many parens. And in Clojure, it's a bit less of a big deal, because you do have the presence of these other data structures, especially vectors. You see it all the time in Clojure code. So that's good. The second thing where Clojure really departs from other lists is that it has this interface called sequence. And you see the word sequence a lot in Clojure circles. It's not a specific data structure. All the four primary data structures are sequences. They implement it. It's a standard interface. And on a practical level, that means that Clojure functions work on all of them to the extent that it makes sense. And this is a huge gain in reuse. And again, it's something where Clojure is a bit different from other Lisps. Generally, other Lisps have functions that only work on lists. And if you want to perform that kind of action on something other than a linked list, then you often will have to use different functions. So here's an example. It's a very common fundamental function in Clojure, conj. So conj just says add a value to this collection. That's it. But it doesn't specify how. So its specific behavior depends on what you use it on. So on the first one, I'm conjing a 1 onto a list, and it adds it to the beginning. That's a comment, by the way, it's semicolon. It adds it to the beginning because that's the most efficient way to add something to a list. And by the way, the apostrophe is there to tell the language, don't run this as a function, don't evaluate it, treat it as data. Because remember, lists have the unique role of not only being data, but also representing code. So we need a way to tell it, I don't actually want you to run that as a function right now, because it would obviously be a problem. 1 is not a function. So yes, on lists, conj adds to the beginning. But for vectors, you can see it adds it to the end. And as I mentioned, vectors are more efficient at adding to the end. Now, conj even works on hash maps, but it would not make sense to conj a 1 onto a hash map. Hash maps are key value pairs. So if you want to conj onto a hash map, you have to pass a vector with 2 values in it, and it will actually just put it inside. And so the end result will be a hash map with 2 key value pairs. So it works on that as well. And finally, conj works on sets, except as you can see here, it just returns a set that's unmodified because it already has a 1. So again, it stays true to the actual data structure, and it has different behavior in each case. But because in all of these cases they implement the sequence abstraction, it'll work in one way or another. Another example this throws people off. Contains is supposed to just return a Boolean that says that it contains a value. For a linked list, though, it throws an error. I forget what the error is, but it doesn't let you do it. The reason why is because it's really inefficient to check if a value exists in a linked list. You have to traverse the entire list until you find it. So Clojure doesn't even bother trying. It's trying to push you to do it the right way. Now, contains does work on a vector, but it doesn't do what you expect. It says contains vector 1, 2, 3, and you're asking, do you contain a 3? And it says false. That's because with a vector, it's much more efficient to check for the existence of a key instead of a value. And so it's checking for the existence of a key. And a key in a vector, of course, is the index. So 0, 1, 2, 3. So if the vector only has 3 items, the index 3 does not exist. Only 0, 1, and 2 exist. So for a hash map, you can see it's returning true because I'm asking, does first exist? Again, with a hash map, it's efficient. It's more efficient to find the existence of a key. So that's what it's doing. And it's saying, well, first is in this hash map, so it's true. Now, we get to a set, and you can see that one actually works the way we wanted it to. It's saying contains 1, 2, 3, 3, and it gives us true. And that's because with a set, there's no distinction between keys and values. Remember, you can think of a set as kind of like a hash map where the key and the value are the same thing. So contains ends up working the way you want. So next question is, well, what if I actually do want to find out if a list or a vector contains 3? Am I out of luck? Well, no. I guess there are a lot of different solutions, but the one that I included here is turn it into a set. If you turn it into a set using the set function, it will work the way you expect. And you think about it, you're like, well, that's kind of roundabout, but in a way, I think this is a really fundamental point about Clojure, which is that it forces you to think about your data structures. It forces you to get your data structures right. If you're using the wrong data structure for the job, you're going to find out because you're not going to get the result you want. So you're constantly thinking about the underlying data structures here. It's like having someone just constantly giving you, computer science lessons on a daily basis. The good news, though, is once you internalize the behaviors, the semantics of all these data structures, it's not like you're constantly running into these problems. Eventually, you're going to realize, oh, if I need to check if a data structure contains a value, maybe I should, use a set. So I think and also, of course, from a performance standpoint, it's pushing you to do the most performant thing. All right. So the second thing was for functional programming. And this is a quote from John Carmack. A large fraction of the flaws in software development are due to programmers not fully understanding all the possible states their code may execute in. And the reason I included that, well, partially it's because I like game development, so, John Carmack. But the other reason is that he spent his career writing C and C++ code, and he started to talk about functional programming. And to me, it's an interesting perspective because this guy, he's been writing software in an imperative fashion, essentially his career. So he has a pretty good perspective on the problems that can cause. That's not to say that he's been doing it wrong, of course. I mean, there are performance characteristics that he needs for games, for high-end games, that functional programming languages have not always been able to do. But nonetheless, he has a really interesting perspective, and that link is an article on Gama Sutra he wrote on how to write C++ in a functional style. And so I wrote C++ for 10 years. I have no idea how to write it in a functional style, but he's John Carmack, so I have no clue what the actual definition of functional programming is, but I'm going to go with immutable data plus first-class functions. That's a good enough definition for me, and it fits on a slide. So, immutability, I'll start with that. That just means copy, don't modify. So here I'm defining a symbol called Nouns, which has a vector in it, and then I'm shuffling it, which just exactly what it sounds like. It's shuffling the contents. Of course, that works on all sequences, as you would expect in Clojure. Now, or I think it does, I didn't check. And Nouns is still 1, 2, 3, 4, 5. So shuffle did not actually affect the original data. And that's just a fundamental aspect of it. If you look at the equivalent in Java, create an array list, 1, 2, 3, 4, 5, you use collections.shuffle, the original data has been modified now. So the original 1, 2, 3, 4, 5 is no longer there. From a practical standpoint, the advantage of the first one is that you have a guarantee that your data is not going to be changed when you run a function on it. Now, if you're a Java programmer, you probably know that collections.shuffle is going to modify Nouns, but what about methods that some random person wrote and you've never read the source code for it? You don't really know what it's going to do to the data that you pass into it. And so this is where it can pull the rug out from under you. And this reaches a fever pitch when you start doing multi-threaded programming, where you could potentially have data being modified from multiple places and multiple threads, and you get the disastrous result that you might expect. So that's the fundamental usefulness of immutability. Now, of course, copy sounds like a pretty expensive operation, but depending on how you implement it, you can do a pretty decent job at it. In Clojure, all these data structures are actually implemented as tree structures, where each time you make a quote-unquote copy, it really is actually reusing a lot of the existing structure. So it's not as expensive as it sounds like, but admittedly, it still is more expensive than direct modifications. The second thing was first-class functions. That just means functions that you can pass as data into other functions. So these are three pretty fundamental functions in Clojure. Map, which takes a function and a collection, and it says, I'm going to apply that function to each item in it. So it's just applying inc, which is increment, to all of those numbers, and you get that result. Filter and remove are opposites. So filter, even, question mark, collection will only return the items that meet that particular function's requirement. And remove does the opposite, obviously. Now, one thing that catches people off guard, you may or may not have noticed, is that all three of these are returning a list, right? Parentheses are lists, but I passed vectors into it. So why is it doing that? This is a source of some annoyance for people. The reason why is because of lazy sequences. So all of the core functions in Clojure, like map and filter, return these lazy sequences, which are basically lists that haven't yet been created. And here's an example of it. So if I define a symbol, Nouns, equal to the value of map inc 1, 2, 3, after that first line, inc has actually not run yet. It has the potential to run. But for now, it's just a lazy sequence that hasn't been realized yet. And then I grab the first item from it using the first function. Well, now it has to realize at least the first item because I'm asking for it. So now it runs inc, but it only runs inc once. It doesn't need to run inc on 2 and 3 because I only asked for the first one. So the first advantage of lazy sequences is that it prevents code from running when it doesn't need to. The other advantage is that you can play with infinity. And so the range function, if you don't pass any arguments into it, it returns an infinite sequence starting at 0. And since it is not a realized, obviously if you were to try to realize it, then you'd run out of memory very quickly. But since it is a lazy sequence, infinity is perfectly natural of a concept. Now, in this case, I'm defining a symbol, all evens, and I'm setting the value to filter, even, range. So range is an infinite sequence. Filter even filters out the odd numbers and leaves only the even numbers. So now I have an infinite sequence starting at 0, but it only includes even numbers. But again, it doesn't need to be realized yet. I haven't run any function on it that requires it to be realized until now. Take 5 all evens. What that does is it says, I want the first 5. Well, now, of course, it has to realize the first 5, but only the first 5. It's not going to run forever. It's just going to run until it gets the first 5, and then it returns it. So now you get a list with 0, 2, 4, 6, 8. So laziness is a useful concept, but that still doesn't answer why specifically lists. Just as in the case with representing code, why specifically are lazy sequences always going to end up as lists? And once again, it's because linked lists happen to be pretty convenient for representing laziness. They don't store an index, unlike the other 3 data structures. Linked lists just have a pointer to the next value. And so it makes a lot more sense from the standpoint of, say, an infinite sequence where you probably don't want to maintain an index of all of them. It makes more sense to represent them as a linked list. But you can just use the vec function to turn it back into vector. I think there's a function mapv which saves you a little bit of typing. But that so I hope that explains why you always seem to get a list when you use these built-in functions. All right. So I mentioned there were 4 things I was going over. This is the 3rd one. Symbiotic with established platforms. That just means it's hosted. It's hosted. The initial primary implementation is on a JVM. There's also Clojure script and CLR, which is .NET. Now, Clojure CLR used to be officially supported, but they got tired of implementing the same thing twice, so they ended up basically leaving it to the community, and I think it's actually being heroically maintained by like one guy, and it's being kept up to date. And you may think, well, what's the point? Why care about .NET? Recently, there's been a project, I didn't mention it on here, called Arcadia, which is using Clojure CLR to allow you to make Clojure games with Unity, which is a very popular game framework based on CLR. So there's at least one really good reason, and of course there are plenty of companies with infrastructure based on the CLR, so they can always make use of that as well. But in terms of the primary officially supported implementations of Clojure, it's really just the JVM version and Clojure script, which compiles down to JavaScript and runs in a browser. And I mentioned here, there are a lot of languages that have ports to the JVM. Ruby and Python have JRuby and Jython, I think, something like that. So the difference with Clojure is that it has nothing but implementations that are hosted. So it's designed from the beginning to be a hosted language. There's no, native, whatever that means, version of Clojure. It's all hosted on various commonly deployed runtimes. And it's a big selling point, this painless interop with Java, for example. So I'm defining a symbol A, and in order to instantiate a Java class, all you have to do is put a period at the end. That's the signal that it is a Java class. So in this case, it's just instantiating an empty array list. And then the period at the beginning of a function name is a way of indicating this is a Java method. And so so .add A1 is equivalent to A.add1 in Java. So literally, if you were to compare that with the Java code, there's like the characters are the exact same, they're just in a different order. And the do-to thing at the bottom is pretty interesting. Do-to is a macro built into Clojure, which will take the A and it will automatically place it here and here, which is kind of like method chaining. If anyone here has used Java, you've probably used APIs where a lot of the methods return the object itself. And the reason it does that is because it's convenient to do object dot whatever, dot whatever, dot whatever. Well, in Clojure, there's just a macro to do that, and it works on everything. So method chaining in Java is something you have to actually create an API for. It doesn't work for everything. In fact, ArrayList does not work that way. But because this is just a macro, it works perfectly with it. So all it's doing there is calling add3 and add4. Now, that's what it looks like with ClojureScript. It looks pretty much the same. So it's called array in ClojureScript, or in JavaScript rather. The only difference here is that you've got this JS/ thing in the beginning. The reason why is JavaScript doesn't really have any concept of packages, namespaces, that kind of thing. Everything's just kind of floating in the global namespace. And so in ClojureScript, it cleans that up by just shoving it all in the JS namespace. And of course, the method names are different. So in JavaScript, the array method for adding is called push. So you would just do .push A1. So, and of course, do2 works with it as well. So if you compare these two, you might be tempted to think, well, is there a way we can abstract these two things so that I can just write code that does this, and it compiles and works on the JVM, and it also works on JavaScript engines? And the answer is it's kind of against the philosophy, so to speak. So Clojure is all about embrace the platform. It's not trying to hide the platform from you and wrap everything in some API that abstracts it away. So most of the time, you're expected to use the underlying functions or methods provided by the platform. If you were to use something that wrapped it, you have problems like it would be slower because you have a layer of indirection that you've added, and now you have to create an entirely new API that is probably a leaky abstraction because it turns out Java and JavaScript are not the same. Nonetheless, that doesn't mean that it's wrong to want to do that. Especially library authors in Clojure often want to write a library that works on the JVM and in browsers with ClojureScript. And so if you're interested in that, there's a project called CLJX. It's just one guy is working on it, as far as I know. And it's an interesting project that helps you to manage the differences. And I know a lot of Clojure libraries are using it so that they can work on both the JVM and in browsers. The reason I included this code sample is because it's a bit of an infamous example in Clojure. Index of is a pretty fundamental function in any language. Find the index of a value in a collection. Turns out Clojure does not have this anywhere. It doesn't implement any kind of index of. And the reason why is because the platforms that it runs on already have an index of. So if you want to use index of, just use the Java interrupt syntax. Remember, the dot in the beginning signals that this is a method call to the platform's API. So what this will do is it will actually call Java's index of method, and it works perfectly with vectors, and so it should return 2. I think it's slightly different with ClojureScript, but you get the idea. So this is a philosophical point, I think, that Clojure has maintained. Another philosophical point, I guess, is that Clojure is really emphasizing the idea that VMs are more important than OSs, especially to companies. Companies have complicated infrastructures, but they don't really care about just using the same OS everywhere. What they care about is using the same VM, such as the JVM or the CLR. That's the thing that really matters to them, because that's ultimately where they're using all of their APIs. And so Clojure can be easily smuggled into these companies, because being on top of these VMs, it can be a situation where you write a small amount of Clojure in a little module somewhere. The rest of your code is Java or C# or whatever. And because of the seamless interop, there's not really any friction. And so this, again, is taken straight from the website. Old way, each language defines its own runtime. New way, language agnostic runtimes. So think of yourself as a company, and you're thinking about what to base your technology on. Well, you could use a language that has its own runtime, but you're limiting your choices if you want to expand to other languages, because chances are they won't be able to interop very easily. Whereas if you use a language agnostic runtime, you can write a bunch of code in Java and later on, write it in Scala or Clojure with very little difficulty. So again, just a point that Clojure is based on. And the last thing is designed for concurrency. And again, I think this is more of a practical feature in Clojure, and one that is definitely relevant today. The first thing people confuse is parallelism and concurrency. The way I think of it is that parallelism is more specific. It's specifically about doing things simultaneously. So you need to have a multi-core processor for that to make sense. Concurrency does not necessarily mean, it's more of an umbrella term. It doesn't necessarily mean running things at the same time. It just means doing things at overlapping times. So if you have, let's say, two different processes, if they're, let's say, overlapping like that on the processor, even if it's a single core processor, that can still count as a concurrent program. So concurrency is relevant even in a single-threaded environment like JavaScript. But first, parallelism. Why does it matter? Supposedly, Moore's law has ended. I don't know if that's true, but I included it. So processors are not increasing single-threaded performance as quickly as they used to for fundamental physical reasons. So to get increased performance, the only other possibility is to run code in parallel. And Clojure has two really useful functions for doing this. pmap, which is the exact same as map, except it actually runs the function you pass into it, potentially in parallel. It completely controls the specifics about like how many threads is it going to use. It bases it on how many cores you have. So pmap inc 1, 2, 3, 4 should do the same thing that map would do, except potentially would run it on separate threads. Now, it wouldn't be that useful in this case, but imagine if you had a collection with, let's say, 1,000 different numbers in it. Maybe pmap would provide better performance than map, and it's literally no extra work on your part. P-values is basically going to let you run any arbitrary function inside of it, and you can put in as many as you want. It's a variadic function, so you can put expensive operations in there, and then once all of them are complete, it'll return a list with all of their return values inside. So it will, it's useful in situations where these two functions were really expensive, because again, just like pmap, it's going to run them on separate threads. So that's parallelism, but again, concurrency is a broader concept. So those two functions don't even exist in ClojureScript, is my understanding, because it doesn't make sense in a browser where it's single-threaded. They're not going to provide any benefit. But concurrency could very well provide you with benefits, even in a browser, because it can still be used as a way to work with issues that come up with race conditions under normal circumstances. So normal values in Clojure are called vars, and they don't really have any concurrency semantics. They're just def nums 1, 2, 3. They're typically what you would use if you don't really expect to change that value. You just want it to stay immutable. The three concurrency types, though, all look the same. They wrap the value. So atoms are away, of allowing you to modify the value immediately. So if you just wrap that 1, 2, 3 vector in an atom, there are some functions that will let you modify it. But it will let you modify it in a thread-safe way, using locks behind the scenes, basically. So refs do the same thing, except they coordinate using software transactional memory, which is something I barely understand. And agents modify a value at some point in the future. They're asynchronous. So if you don't necessarily need to modify it now, they provide a different set of semantics that might help you solve your problem. To be honest, I barely have used refs and agents. If you have a particular problem where that makes sense, then you'll be happy to have them. Most of the time I find myself just using atoms because they're the simplest. They're just a way of providing you with the same thing you would get in a mutable language, but in a safer way. So I'll just talk about them. Atoms look like that. Def nums, atom, 1, 2, 3. Now, nums in this situation is not a vector. So if you try to conj onto it, for example, it's not going to work. It's an atom. If you want to actually get the vector inside of it, you have to call deref. And so that pulls it out. You can also just use the @ symbol. It's just a shorthand way of doing the same thing as deref, because it's very common to want to do that. And if you actually want to modify the value inside of it, reset is the simplest. It just wipes out the value and replaces it with something else. So reset nums 4, 5, 6 will just reset the value to that new vector. Swap is a bit more sophisticated. So instead of just resetting it, it will let you modify the value by passing a function along with 0 or more arguments. So in this case, I'm swapping nums with the conj function that we saw earlier. And I want to conj 7 and 8 onto it. And since we learned before that vectors are most efficient at appending at the end, that's exactly what it's going to do. It's going to swap nums, and it's going to conj those two onto the very end. So, I mean, that pretty much is an atom. So that's all 4 things I wanted to discuss. A Lisp for functional programming, symbiotic with an established platform, and designed for concurrency. So I haven't talked at all about the tooling because I thought it was a bit out of the scope here. But nonetheless, if you just want to use a plain text editor with Emacs or Vim or Lighttable, you would install Linigan, which is the main build tool of Clojure. You can also just use the Clojure IDE, which all 3 of these include a copy of Linigan inside of them. So it might be a bit easier to get started with. Counterclockwise, if you want to use Eclipse, is a plugin. Cursive is a plugin for IntelliJ. And Nightcode is what I mentioned, the one that I made. It's not a plugin for anything. It's a standalone project. It's a lot more basic than the other 2. Like it's meant for beginners. So if you want the features of the other 2, then they would probably work better for you. So that's my email. That's my GitHub. If you're interested in games, Nightmod is the tool I mentioned that is specifically focused on game development in Clojure. And I'm also doing a talk at ClojureCon in a little over a week called Making Games at Runtime with Clojure. That's why I was actually happy to fill in for Ben, because I needed practice, because I'm a nervous wreck about that. So that's about it. I mean, if you want to see other specific examples or you have questions, let me know.